Um, so yeah, welcome everyone. We have the privilege to get a nice short course from Dinesh Prabhu today on CFD for capsule design. So I'll give a quick bio of Dinesh, and then I'll hand the floor over to him to let him begin his talk. Dr. Prabhu attained the bachelor's in aerospace engineering from the Indian Institute of Technology, and then later a master's and PhD in aerospace engineering from Iowa State University. He's currently a senior research scientist at NASA Ames Research Center. And he's worked on a number of different projects over the years, including the X-33, X-37 Space Shuttle Orbiter, to name many. MSL, Mars 2020, he's currently working on MSR. And so I will let him talk more about that. I guess he can speak much better about that. So without further ado, please, Dinesh, go ahead.
Thanks, JB. Good afternoon, everyone. It's still morning for me here. Okay. Adam and JB contacted me for a short course and used a rather broad title. And the title chosen at the unofficial title at that time was CFD for capsule design. Didn't pay much attention to it until about a week ago when I started putting together slides, and then found that this to be way, way broader scope. So I decided to narrow the scope down a bit, and here is the unofficial title. If I can move my slide forward. Narrowed the scope down considerably, so the unofficial title is CFD for aerothermal design of capsules for atmospheric entries at the ice giants. It's a little different. It's a simpler system, I think. And I'll try and walk through the whole process here. What you will not hear in this talk is anything about algorithms or languages or hardware improvements that we could use. It is simply application of the current models that exist within computational codes and apply them to the specific case of atmospheric entries at the ice giants. That said, just filling in the bio, the career path that's, oh, and JB forgot to mention, all my degrees are from the previous century. And currently, and the career path there is littered with several other projects that are not listed here because they were mostly canceled. And there were some proposals that we did have wins in. Anyway, so moving right along, what do we need to know? This is a leftover slide from a seminar last summer. What do we need to know? We need to know the destination that we are headed to. And essentially, it's to get an estimate of the kinetic energy of entry and see how that energy stacks up against chemical bond energies, if you will. We would need to know the entry vehicle geometry. The shape determines the aerodynamic drag, and the size determines the drag area, which along with the mass then translates into a ballistic coefficient, which is important. We would need to know trajectory or trajectories that this entry vehicle geometry is likely to fly in the atmosphere. And we would need to know the dispersions, either due to dispersions in the entry state or the uncertainties in either the atmosphere or aerodynamics. Once we have these three, we then use our computing tools. We compute for flow fields primarily, and radiation fields if they are applicable. Fortunately, it turns out for the ice giants, radiation is not particularly a concern, at least up to a certain entry velocity. And we would also need to know, we would need to have access to material thermal response codes. I'll give you some examples without getting into specifics of materials. But primarily, the use of CFD in design process is the scaling laws that we can derive from the computational work so that we can do rapid trades, at least at a conceptual design stage. And the focus would then be on just the pressure and convective heat flux. To give you an idea of, give you a little bit of history of exploration of the outer planets, there are four: Jupiter, Saturn, Uranus, and Neptune. And Jupiter and Saturn have had several missions that have done either remote sensing and in the of the atmosphere of the planets, or in the case of Jupiter, we had the Galileo mission, in which actually in situ measurements of the atmosphere were made using a descent probe. The first two are gas giants, and the last two are ice giants. And the one happy development is that Uranus now figures as a high priority flagship mission in the most recent decadal survey. Now, Jupiter's, it's although Pioneer 10, 11, Voyager 1 and 2 went past Jupiter, if Jupiter is used in gravity assist, for example, Cassini, then that mission 2 would have some remote observations of the planet. Now, Cassini was deorbited and did enter Saturn's atmosphere, but no atmospheric measurements were made. And I believe a similar fate awaits Juno, and it too will be deorbited for entry into Jupiter. Now we'll pick up, this is just the history bit. If you look at the characteristics of the outer planets, and this is where some of the challenges are, this is a pretty dense table. So let me walk you through column by column. There are 4 destinations listed in column 1, starting with Jupiter and ending at Neptune. The escape velocities of the planets are listed, and you'll see Jupiter has a fantastic escape velocity of 60.2 kilometers a second. Now, the first 2 planets, the Saturn and Jupiter, spin like tops. So if you look at column number 3, it's the rotational velocity of the atmosphere. And Jupiter and Saturn have something of the order of 10 kilometers a second or more. Uranus and Neptune, on the other hand, spin a little slower. The whole point, and column number 4, these are representative inertial entry velocities at those planets. So at Jupiter, the inertial entry velocity is roughly 60 kilometers a second, almost its escape velocity are slightly lower. And okay, mind you, all of these entry velocities listed here assume direct entry into the planet's atmosphere. So there would be a carrier spacecraft that would release a probe into the atmosphere, and then the probe, as it descends through the atmosphere, would telemeter data back to this carrier and relay spacecraft. It could be an orbiter with further mission longevity to it. But for right now, we'll assume these are direct entry velocities. And if you enter the atmosphere with the spin of the planet, then there are benefits to it because you reduce your relative velocity of entry. And you have that ranging from about 48 kilometers a second at Jupiter down to something nicer at like 20 and 25 at Uranus and Neptune. Now, if I simply take the 1/2 v squared of that column, I get a reference kinetic energy, which is shown in column number 6. Look at those numbers. If you look at Jupiter, the reference kinetic energy is an unbelievable 1.1 gigajoules per kilogram. And that Galileo accomplished that mission is just an amazing feat. The other 3 destinations, the kinetic energies are large, much larger than what we would have at Earth, because think about it this way. Stardust came in at roughly 12.5 kilometers a second, which is small compared to these numbers that you see in column number 6. And I have the composition listed, and all four destinations, the primary constituents of the atmosphere are hydrogen and helium. Although at Uranus and Neptune, there is an additional trace amount of methane in the atmosphere. This is per the current modeling that we have for these destinations. The last two columns are the more interesting ones, and I've listed the bond dissociation energy. That is the energy required to split a molecule into its constituent atoms. And if you look at the numbers for hydrogen and methane, those numbers are pretty small compared to the amount of kinetic energy that you have at entry. The last column is significant, and that is the ionization potential for each of those species. And those numbers are large compared to the kinetic energies of entry. Now, these are quick first estimates for you to decide on the importance of each. So if you look at the ionization potentials, you can see that Jupiter gets up close to that level. So you would expect that atmospheric entries at Jupiter would be dominated by either atom lines or by a continuum due to ionization. And indeed, Jupiter, the entire entry is driven by radiative heating. Whereas for the other planets, Saturn, there would be some amount of it, but for Uranus and Neptune, it's unlikely that you would have radiative heating, which is a good thing. So it simplifies life just a little. One other thing to point out is that entering a planet's atmosphere with the direction, in the direction of its spin, or what are called prograde entries, is definitely beneficial because you get a reduced aerothermal environment simply by reduction in velocity relative to the atmosphere. The maximum benefit of planet rotation is at the equator of the planet, and the benefit drops off as the cosine of the latitude. So if you had polar entries, then there is really no benefit that you would get from the spin of the planet. And typically, science would be of interest at higher latitudes rather than at the equator, but you have to make that trade-off, and that's a mission science decision on what latitude you would want to go to. And a couple of rules of thumb here: if you entered Saturn in a retrograde fashion, that is, you go against the spin of the planet, then you're looking at an entry that is similar to that of a prograde entry at Jupiter. So it becomes very complex. Similarly, if you entered Neptune in a retrograde fashion, then the entry would be similar to a prograde entry at Saturn. Okay, so as I said, for ice giants, the entry kinetic energy that you have, at least based on the current missions that we've looked at, there is no energy that's sufficient to ionize gas species. Convective heating would be the dominant heating mechanism, and there would be no radiative heating until you exceed entry velocities of 27 kilometers a second. So entries into ice giants, I think, makes our life just a little easier. That said, we do need to look at the atmospheric structure of the two planets. And atmospheric structure, you can look at it in two ways. One is the thermal structure of the vertical temperature distribution in the atmosphere, and the other is its composition. So in this slide, what's shown is the typical pressure temperature graph for the planet. The symbols shown for both planets are the data that were acquired by Voyager 2. And the solid lines are models, two different models of the atmosphere. The green line is what is currently incorporated into a code called TRAJ at NASA Ames. And the blue line is a model representation. And in any case, underneath the title of each slide, I have put in the corresponding references in case people are interested. Now, on this, pick any of these two. Let's pick Uranus. There are several sets of dashed lines indicated at various pressure levels. Working from the bottom upward, the dashed line shown corresponding to 1 bar or 1,000 millibar is the reference altitude. There is no surface on any of these gas planets. So we pick arbitrarily a altitude of 0 kilometers that corresponds to a pressure of one bar or 1,000 millibar. Now, it turns out the interesting part is that almost all the gas Isen gas giants have their tropopause at roughly 100 millibar. Okay, and that's shown as the other dotted line over there, which is an approximation to it's not a hard number that that the tropopause has to occur at 100 millibars. But the point here is this: you would start mission science from tropopause and sink the descent probe to 10 bar, which is the limit shown here, although Galileo sank down to about 20 bars or so. And beyond that, the atmosphere becomes opaque to RF transmission. Hydrogen becomes opaque to it. So you cannot extract data much deeper than 25 bars or so. So your trajectory would be that you would release the descent probe at around tropopause, which means you try to achieve Mach 0.8, which is your parachute deployment Mach number, at roughly 100 millibars or so. Now, a typical trajectory, peak convective heating is shown as the purple dotted box, and that occurs somewhere between 10 millibars to about 40 millibars. Okay, so it's a rough estimate of where peak heating is likely to occur. So based on the trajectories that we have looked at to date. Now, the final line that's shown at roughly 10 to the minus 4 millibar is what would be considered the entry interface altitude. For Neptune, that line looks okay. For Uranus, it does not. I think it should sink lower than 800 kilometers where I've shown. Okay, I've done the mapping already. I have not shown the pressure to altitude mapping in this case. Okay, this is the thermal structure. The nice point of the thermal structure is where peak heating occurs. If you look at the ambient temperature in the atmosphere, it's less than 100 Kelvin. So it's between 50 and 100 Kelvin. It's around 50-ish Kelvin for the case of Uranus, and it's about 60 to 70 Kelvin at Neptune. Assuming that you had absolutely no dissociation, no chemistry going on, and you had just frozen flow, you can use your simple gas dynamic relations to estimate what a post-shock temperature would be behind a normal shock. And let's assume that your Mach number is of the order of 30-ish, between 25 and 30 at peak convective heating. And if you work out what that post-shock temperature would be, it would be of the order of 15,000 Kelvin or less. And this is for frozen flow. So which means if you had chemical reactions, you should expect that temperature to be much lower, and hence there would be little to no radiative heating, but there will be a significant amount of convective heating simply because the Reynolds numbers are so high. Let's look at the compositional structure. And here's where things get a little messy because you have to rely on models to determine what the composition would be. You do know the pressure and temperature from the structure, but in order for you to reconstruct a density profile, you would need to know the composition which you would then use in an ideal gas equation of state to back out density. And the models based on photolysis of hydrocarbons in the atmosphere, that's shown in that Julian Moses and others have done in the paper referenced there. You'll see that for Uranus, there is really no CH4 in the atmosphere, at least not to the level of 0.0001 mole of it. For Neptune, there is. So if you overlay the same peak convective heating box, you'll see that Uranus, you can get away with just hydrogen and helium as the gas composition. In Neptune, you probably could get away with it, but if you do need to include methane, then methane is of the order of 0.0015-ish moles. It's a small number, so it's unlikely to make a big difference. But really what I would like to point to is in the Uranus chart, you'll see that above a pressure level of 0.1 millibar, there is unmixing of the atmosphere. Really, you rely on the turbulent eddies within an atmosphere mixing the constituent gases thoroughly so that it's a homogeneous composition. Above that, once you lose the eddy diffusivity of the atmosphere, then molecular diffusivity starts separating out species. And so you'll see an altitude above which lighter species now start to rise very rapidly away from that boundary. So in the case of Uranus at 10 to the minus 4 or so, you'll see a rapid increase in hydrogen with a corresponding decrease in helium. And bulk of the atmosphere then is still hydrogen. So your lighter elements would be at the top of the atmosphere, and the heavier element, in this case helium, would be deeper inside the atmosphere. However, that said, for initial analysis purposes, we can assume that for Uranus, you have 8515 in terms of mole fractions as the composition of the atmosphere, and 8218 as the composition for Neptune. So we do know what the atmospheres are like to start our analysis. So the next question is, what should the capsule geometry be? Typically, you would rely on heritage, and the heritage for exploration of planetary atmospheres is usually a 45-degree sphere cone. And what's shown here are three examples of 45 degrees of sphere cones. And working from right to left in the figure, the first one shown as Hayabusa, which is an Earth entry capsule. In the middle, you have Galileo. And on the far left, you have the shape that was used in the Pioneer Venus mission. And the reason for a 45-degree sphere cone is that it has good dynamic stability characteristics that you need to worry about. And in all of these destinations, unlike Mars, you have density in your favor. So it's not a tenuous atmosphere where you have to worry about impact with the surface. And so it's okay to consider a 45-degree sphere cone. Now, Deep Space 2, which was on Mars Polar Lander, was also a 45-degree sphere cone, but unfortunately, the MPL mission failed, and we really don't have a flight heritage for the 45-degree sphere cone at Mars. Now, it's often claimed that the nose radius to base radius has to be a ratio of 0.5, which is not necessarily true. It's a trade-off between how sharp or how blunt the cone has to be. A sharper nose would be preferred if shock layer is the dominant heating mechanism, because radiative heating goes directly as the square root of the nose radius. A blunter nose is preferred if convective heating is the dominant heating mechanism, because convective heating, as everyone knows, goes as 1 over the square root of nose radius. So the larger you make the nose radius, the lower your convective heating. And we can use this knowledge in early conceptual studies and working with different bluntnesses, and I will get to that towards the end of the talk. In any case, so the one in the middle then forms the basis for atmospheric exploration of the ice giants, with the nose radius being left as an open parameter of choice, and we can work with different blunting for a similar size capsule. So we assume here that we are going to carry the same types of instruments that were carried aboard Galileo. So the size or the diameter would then depend on how well you can package this and where you place the CG of the capsule. So we have the atmosphere now, we have the capsule geometry, and even before you do CFD, you can get some very quick first estimates. And the first estimates are easy to obtain because direct entries into the gas or ice giants are almost always ballistic. There is no lift, which implies there is no angle of attack for an axisymmetric geometry. The entry capsule is spun up before release, and it's spin stabilized through the atmospheric entry phase. It's passive. There is no control on this capsule. Now, the very simple view that one could take is the atmospheric density reduces the velocity magnitude, and gravity helps turn the velocity vector. And so in terms of CFD, we only need to worry about the atmospheric density profile and the trajectory that's flown through that density profile. Now, if we make a further restriction that we are not worried about any change in flight path angle, and we have a constant temperature atmosphere, both of which you really will not be able to meet, but at least you would get closed form solutions for certain things. And the most important couple of quantities, most important is the product here, which is ambient density raised to some exponent A, and the flight velocity, flight speed raised to an exponent B. So you can determine when that product reaches a maximum, and that reaches a maximum when the flight velocity is VE times the exponent minus A by B. So now you have a quick and dirty estimate of where peak heating is going to occur and where peak stagnation pressure is going to occur. If you assume that peak heating goes as rho to the half power and V cubed, then you can say that it would occur when the flight velocity reaches about 85% of its entry velocity. So you've lost 15% of your velocity by the time at the time of peak heating. And similarly, you would achieve peak stagnation pressure when you've lost about roughly 40% of your entry velocity. Okay, these are first quick and dirty estimates of what you're likely to encounter. Now, you would typically have a single flight trajectory, and you can easily compute the physical quantities of interest through CFD. So all you do is discretize the heat pulse and stagnation pressure time histories, and you perform flow computations at these trajectory points. When you have multiple trajectories, okay, in the case of a single trajectory, the trajectory of interest would be the one that gives you the maximum heat load, because the maximum heat load determines the thickness of the thermal protection system, and the material that you would choose is fairly straightforward and known. It would be some carbon-based ablator, the density of which will depend on the magnitude of heating that you would see. So your choices would be pica or heat, which is a new material, either in a single layer version or a dual layer version, or full density carbon phenolic, which was what was flown on Galileo, and that last material is no longer manufactured, at least not to the NASA spec. It's still used in the DoD world. Now, if you had multiple trajectories, where you now include atmospheric dispersions, aerodynamic uncertainties, and uncertainties in the entry state, then you can't simply discretize each flight trajectory and perform CFD computation at every one of those discrete points. Instead, you would switch over to a design space idea, and the intent there is to de-link trajectories from the environments and then use some sort of scaling law or interpolation technique based on scaling law that would help you reconstruct trajectories, environments along a specific trajectory. Now, what we are tacitly assuming there that there isn't any substantial shape change due to material recession. So this is certainly not true for Jupiter entries, but it's a useful assumption for ice giants. And to give you an idea of what a single trajectory would be discretized, I've shown an example of a Neptune trajectory. Once you have the density and velocity that's provided by your trajectory code, you can simply use correlations for the stagnation point to come up with these heat and pressure pulses. And then you can select points along these two pulses, pressure and heat, and perform CFD at those points because you know the density and the velocity at each one of those symbols that are shown there. Now, the only trouble here is if you have access only to a continuum code, then you closing the heat pulse or the pressure pulse to especially the heat pulse, to early time becomes difficult because you have more and more rarefied flow and the Knudsen number becomes higher and higher. So you would be forced to use a DSMC type approach in the early trajectory times. Now, all of these correlations here, for the pressure, it's Newtonian impact theory that would give you a first estimate of stagnation pressure. And for heat flux, you would extrapolate a first order boundary layer experience all the way into low density atmosphere as well. And I've shown an example of a design space in air. So the broad swath of orange and black lines actually represent 5,000 trajectories each. So those 10,000 trajectories are then encapsulated within 3 trajectories constructed to make a design space. And you discretize those constraining trajectories so that if you have a flight trajectory that fell between these points, then you can use the environments that you've computed at the open symbols through some means to, using scaling laws essentially, to construct the aerothermal environments at the trajectory of interest. Now, you do impose upper and lower limits depending on what kind of CFD code you have. At the upper limit, you would use a Knudsen number cutoff. Again, this varies from person to person on what you think the highest Knudsen number should be for continuum flow. And the Knudsen number being the mean free path of the molecules in the atmosphere, referenced to some length scale. And the length scale of choice is really the nose radius. For a ballistic entry, that should be the characteristic length. So the limit number, 0.01 or 0.001, is subjective, but it represents the limit up to which the continuum approximation holds. The lower limit would really be your Mach number cutoff. It should be at parachute deploy. So let's say roughly Mach 1. It's also subjective. And you have to remember, as you get to a lower and lower Mach number, your solver has to now deal with diminishing compressibility of the flow medium. Now, additional guides you get are through equilibrium estimates of the post-shock composition. So we have a way of handling trajectories. So we have the destination given, we have a shape given, we have trajectories given, and so we are ready to do a little bit of flow modeling and solve the flow equations. So like I said before, you have to decide between continuum versus non-continuum. I tend to be conservative in my choice of Knudsen number. So I assume 0.003 as a rough limit for up to which I can possibly push a continuum code. Above that number, I would resort to using DSMC code. Of course, there would be some region where you would perform both DSMC and continuum calculations so that you have a fairly smooth handoff from one regime to the other. What are the list of species for ice giants is very simple. It's hydrogen, both in its molecular and atomic form, and helium. For the case of Neptune, you might have to consider methane and its dissociation products. Okay, we have a list of products. We do need to know what the chemistry mechanism is and what the reaction rates are. So you have to deal with chemical kinetics in the shock layer. That's another field of study. You would, of course, need thermodynamic properties of the constituent species and a way to mix those properties to come up with the properties of the mixture. You would need laminar and turbulent transport properties of both constituent species and mixture. But the biggest issue is, and we have models for each one of these. We have thermodynamic properties, we have turbulence models, mostly all fluid mechanics based. Really, the issue is one of wall boundary conditions. What should you use? Whether you should consider a cold wall or a hot wall, or if you allow for a hot wall, you don't need to know what the recombinative efficiency is, which we tend to call as catalytic efficiency, versus an equilibrium wall. And finally, you do also need to know something about the surface morphology, the surface roughness, because that can augment turbulent heating. So this is a general idea. Now, getting down to nitty-gritty, the entry problem really is one of transformation of energy between four different modes. And the four modes are thermal, chemical, radiative, which we can ignore for the ice giants, and kinetic energy. And how do you manage these 3 to 4 modes using a thermal protection system? Now, when you say energy, what is really meant is the total enthalpy of the gas mixture. And that total enthalpy you can divide into three parts. One is the thermal part, one is a chemical part, and the third part is, of course, the kinetic energy. Okay. Usually the thermal enthalpy content in the ambient gas is negligibly small. That is because your ambient gas temperatures are very, very low. In the case of ice giants, it's less than 100 Kelvin. In the chemical mode, if you're looking at hydrogen and helium, you really don't have to worry about those in the ambient gas. But in the case of CO2 atmosphere, which is primarily Venus and Mars, you do have to consider that because CO2 has a very high heat of formation, about roughly 9 megajoules per kilogram. So the atmospheric entry problem, what you really do is take your ambient gas and you shock heat it using the bow shock that forms around the atmosphere and essentially convert the high kinetic energy in the free stream. You reduce it considerably and convert that into chemical and thermal energy. And the chemical energy is what you recover at the surface, along with heating due to the shear layer on the surface. Now, your consideration in designing trajectories should also factor in ArcJet testing, because you cannot come up with environments that cannot be tested on the ground. And so in an ArcJet test, you take low kinetic energy ambient gas, and instead of bow shock heating it, you arc heat it. And that dissociated gas then acquires kinetic energy in a convergent divergent nozzle. And there's a limit to which you can have a nozzle expansion. And you reduce the thermal energy due to the expansion, but you acquire a good bit of kinetic energy. Now, that kinetic energy is reduced again behind the bow shock around the test article, and then you recover chemical energy at the surface again. So these ideas need to be factored into coming up with a trajectory that meets both mission constraints as well as ground testing constraints. The principles of CFD are fairly straightforward. There are only three conservation equations that you need to worry about. The first one is mass conservation. There are as many mass conservations as you have number of species. So for a species S, in steady flow, you have the equation as shown up there. That's the equation you would solve with the CFD code. It's very easy to write this down, but there's some devil in details here. And the two things that you need to really worry about are the mass diffusion coefficient and the production rate of species, of each species. So you do need models for that. Now, mass diffusion coefficient for a ice giant is easy. It's at best binary because you have only H2 molecule and HE, or at worst, it's ternary, where you have three species, H2H and HE. So for initial computations, it's probably a good idea to simply assume you have a constant Schmidt number from which you can then work out what the diffusion coefficient ought to be. Or if you want to get really a little more precision in the physical model, you can rely on collision integrals. And lots of computations are being done for various different collision pairs, and those data are available in modern CFD codes. What you really need, the more important thing here, is the chemistry mechanism and the kinetics, and that requires some doing. The chemistry mechanism, I think, for Uranus is fairly straightforward. There's only one reaction to consider, and that is the dissociation of molecular hydrogen into its two atoms. So that's the first one that's highlighted. Now you can get a little more fancy, assuming that you have ionization. So you have either associative ionization or direct electron impact ionization, which is then modeled as a two-step process. I think for Uranus entries, the last 6 reactions are superfluous. And all of these reactions are written in the endothermic direction, which is the energy supply direction. Easier to visualize. Although codes are neutral, you provide a reaction rate and you provide an equilibrium constant, it can back out the other. So you provide either the forward rate and an equilibrium constant or a backward rate and equilibrium constant, and you can work out what those corresponding backward or forward rate would be. And the reaction rates are usually written in a modified Arrhenius form that are shown. Now the A, N, and TA parameters that are shown in the equation are constants and typically would be determined through shock tube experiments or some other means of getting there. Now, the activation temperatures are easy to compute. You can compute them from heats of reaction for each of those reactions that are shown there. But you have to remember that those heats of reaction, you assume there are no thermal barriers. Indeed, for any of these, there aren't gigantic thermal barriers as you would get in a CO2 environment, where CO oxidation does require the use of a catalyst. So there's no catalysis worries here. So that takes care of the Momentum conservation is very easy. So steady flow, what's shown here are inertial terms against a diffusive term, which is simply divergence of your stress tensor. And the stress tensor is just a vector gradient of velocity. And the key things here, you need to have an equation of state that links pressure to density and temperature and molar mass, which is m. And you need to know what the mixture coefficient of viscosity is. Now, viscosity for each species comes from collision integrals from pairs of species. The classical approach in the past has been to use a Lennard-Jones 612 potential, and I'll show you the impact of assuming that and why it becomes an issue in comparing CFD results with older data. And of course, you need to know how to get the viscosity of the mixture. And this does play into how well you can predict what the heat flux ought to be. You either rely on a classical mixing rule of Wilke or you use Gupta-Yos, and one of them could be more dissipative than the other and lead to increased heating. So momentum conservation is easy. Really, bulk of the idea here in hypersonic competitions is in the energy equation. So the steady energy equation is shown here in terms of total enthalpy, which is a little different than what people are used to seeing, because typically you would see that in terms of total internal energy or ET. But if you used H, there are some benefits here. When you write this equation, you can handle any sort of gas mixture, including ones that have negative heat of formation. So way to handle that is you can subtract out that negative heat of formation from your total enthalpy. You wouldn't alter the balance that's shown in the equation above, and it makes everything positive. Only thing is you've got to remember to put it back in when you compute the temperature from enthalpy. The nice part here is if your viscous terms are small, that is, you have very high Reynolds numbers like you would at the ice giants, then the diffusive terms on the right-hand side of the equation on top can be neglected, and essentially you have a divergence equal to zero, and total enthalpy is a constant. And that is a result that you could use in defining the boundary layer edge, which is distinct when you have high Reynolds numbers, but at low density flow where you have a strongly interacting boundary layer, then it becomes a little more dicey on what the boundary layer edge ought to be, because it's no longer a shear layer that's driven simply by pressure gradient, but it is a shear layer that can communicate with the inviscid part through the normal momentum equation. Now, the key thing in here is specific enthalpy of each species, and that you get from either NASA Lewis fits or you get from curve fits that have been developed by Capitelli's group. The key point here is the NASA Lewis fits have a lower temperature limit of 200 Kelvin. So you have to be careful with that. And what we currently employ is simply extrapolate enthalpy linearly at low temperature, essentially making the assumption that specific heat is a constant at low temperatures. Now, this is not necessarily true for hydrogen atmospheres below 300 Kelvin. You do have to account for the ortho and para forms of hydrogen, what impact they have on our final result, we don't know. But what we assume is it doesn't matter what the free stream ambient gas is, because it is shock heated anyway, and the post-shock temperatures are going to be much higher than 300 Kelvin. And so we can get by with using this linear extrapolation technique. What I have not done yet is to look at the data that have been provided by Capitelli's group, which have a lower limit of 50 Kelvin. Those would be something to explore in the future. Now, to give you a visual picture of what the thermodynamic and transport properties look like, on the top row, I've shown the specific heat of each species as a function of temperature. There are two sources of data there. One is what is in the NASA Lewis code, CEA, and what's in DPLR, the CFD code that we use here at Ames. And there's pretty good agreement between those two data with the tables that were painstakingly computed by Gurevich and others in Russia. Point here is this: if you're not going to see post-shock temperatures any greater than 15,000, then for all practical purposes, hydrogen atom and helium have constant specific heats. And most of the energy management is done by the hydrogen molecule, which has a pretty fantastic specific heat that rises up. So it can take quite a beating before it comes apart. Transport properties is a different kettle of fish. There are three sources of data that I've shown here. The blue line is the classic data using a Lennard-Jones potential, and that's what is the basis of Sutton and Graves' work for stag point correlations. The green and red lines, the green line comes from Svela's data. That's what's in the CEA code. And the red line is unpublished work of Mike Wright, and those are based on collision integrals that were computed. Now, Svela's data and the data of Wright, which is incorporated in DPLR, agree quite well. Mind you, at low temperatures, where we do have experimental data, you can get that in your CRC handbook, for H2 and helium, it doesn't matter. Any of these three models would work, but it's in the high temperature region where you shouldn't use Lennard-Jones potential as the representative intermolecular potential to compute collision integrals. The somewhat disturbing trend that I see is the inflection in the red curve for the hydrogen molecule. It doesn't agree with the data of Svela, and it shows an inflection that is kind of uncomfortable. But I think viscosity should be a monotonic function with no inflections. That is, you can represent it using a power law, but this is where we stand. So this needs some examination. Although the variation against CEA is pretty small, maybe we can get away with it. So we have properties done, we have all of the information we need to turn the CFD crank. But before we do that, we need to look at boundary conditions. Two of those boundary conditions are easy. You have a no-slip boundary condition, and you have a pressure gradient in the wall normal direction set to 0. So those are not particularly of interest. But we need to consider three types of walls. You can either have a cold wall, a hot wall, or an equilibrium wall. In a cold wall, you fix the wall temperature at 298 Kelvin. And 298 Kelvin, even if you're going into a hydrogen-helium atmosphere, 298 Kelvin is the number to use if you're using CEA, because that is the reference temperature that guarantees you that you have a zero enthalpy by definition. Enthalpy is a delta quantity, by the way, so it doesn't matter, but it depends on what you choose as your reference. 298 Kelvin would be the preferred reference. So you fix the wall temperature and you compute the species chemistry. You allow that to float. But at such a low temperature, given that there is no thermal barrier to H plus H recombining. It's a very tenable physical boundary condition to employ. You could choose to use that. The cold wall boundary condition comes in handy for you to determine what your test conditions should be in the arc jet. Typically, you would take a hot wall result and you would put some factor on it to come up with what the cold wall result should be, and then determine your arc jet setting for that cold wall result that you came up with. But this using a cold wall model gives you directly what the heat flux you should be testing at in the arc jet. Now, the hot wall, you allow both the wall temperature and species chemistry to float. The problem here is you usually ignore the conduction into the material. So you say that the wall material is only capable of cooling by re-radiation, and the efficiency of that re-radiation is the emissivity of the surface. So you re-radiate all the incident heat to a low temperature sink, and typically in CFD codes, that sink temperature is 0 Kelvin. You could, in principle, have a different sink temperature, but it wouldn't matter. And that emissivity then is temperature dependent. So what should the wall composition be in such a model? You then say, okay, I'm going to allow hydrogen atoms to recombine, and the process of recombination is going to release heat and heat the surface. And I set the gradients of molecular species to 0, or even helium, which is inert. Now, the heat of reaction of hydrogen recombination is pretty high. It's 436 kilojoules per mole that you would recover at the surface. Here you have a problem because you assume that all of this is in gas phase, and you don't temper this gas phase reaction without a corresponding equilibrium constant. So what happens then is the temperature, the energy balance that you have in re-radiation could end up with a temperature that is much higher than the sublimation temperature of carbon. You could control to some extent this first order gas phase reaction through an efficiency parameter. And when you set that efficiency parameter to 1, you refer to it as a fully catalytic wall. And when you set it to 0, you refer to it as a non-catalytic wall. Here, the notion of catalysis is somewhat hazy because really there is no thermal barrier to the hydrogen recombination reaction that has to be mediated by a catalyst represented by the surface material. The easier fix, in my opinion, is to work with an equilibrium wall. So you have a P wall determined by your dP by dN equals 0 boundary condition, and you allow T wall to float, but you assume given P and T wall, you can work out given two state variables, you know what the composition is going to be, and hence you can come up with what the equilibrium composition at the wall is. And this is between a cold wall and equilibrium wall. For a hot wall case, I would then prefer to use an equilibrium wall. Now, the equilibrium wall, you have to wonder when thermodynamic equilibrium is applicable. Typically, one would say that, okay, 1 bar or more of wall pressure is where equilibrium is a tenable assumption, but you can extend it to lower densities as well. So this would be a thing for research in the future. Now, this equilibrium wall idea works quite well, except for CO2. And the reason for that is CO plus O has a significant thermal barrier, and you do need a catalyst to mediate and that reaction by reducing the thermal barrier. And that's the basis for catalytic converters in cars. But we don't have to worry about CO2 in the ice giant atmosphere. So we have boundary conditions. And this is the same idea, reiterating the same idea. What essentially you're doing is you're taking the flux of H atoms and you're driving that as dependent on the surface temperature. So this is the flux of atoms arriving at the surface. You can incorporate that into your governing equations. And the gamma H is the recombination efficiency or catalytic efficiency, as people call it. And depending on whether you have experimental data or not, that gamma H could be temperature dependent, and it would also vary from material to material. Really, what we do need to look at is gas and surface interaction of atomic hydrogen with hot carbon, which represents the heated vehicle surface. So we assume for now that we can exercise either cold or hot wall or an equilibrium wall in the CFD calculations. Finally, there's the idea of transition. A conservative approach to developing a design database is posited on assuming a fully turbulent flow that gives you the highest amount of heating, although you don't have to, although it's not going to matter much in terms of material choice, but the heat load that is imposed would affect the sizing of the material. And so you would work with a turbulent flow heat load on the material. Now, can you remove some of that conservatism by considering flow transition? So you have part of the heat shield is laminar and the remaining part is turbulent. So that could change in some way and reduce the amount of TPS mass. So you have to worry about two things now. One is, where does the transition occur on a smooth wall? And that transition is due to instability of the wall-bounded shear layer. And one criterion to use is the Reynolds number based on momentum thickness. And you say that at any point on the vehicle and at any time instant t, if that RE theta value exceeds 250, then you have transition from a laminar boundary layer to a fully turbulent boundary layer. You could work out a transition model and put in a transition length in the CFD calculation, but this is a typical criterion. Or if you had a rough wall, you could have a sand grain based rough wall criterion, which is REKK. And the key thing in here to note is the density and velocity for K are evaluated at the top of the roughness height, but the viscosity that you use is the wall viscosity, not the value of viscosity at the top of the scale height. And the reason you're doing that is you're extracting REKK from a smooth wall laminar solution. And at that point, the probe point is a virtual roughness point, if you will, and roughness is part of the wall. In any case, REKK, you claim that as if it exceeds a value of 200, then you have transition. Both of these criteria have experimental data to back them, one or the other. The one take that I have is roughness usually develops in time, but for design purposes, we assume that it's constant over the entire flight. So it then remains that once you have CFD solutions, how do you get to these things? We do use a code called B-layer, which helps you determine the boundary layer edge as well as compute integral parameters like momentum thickness and displacement thickness. So With that long-winded preamble, here's a more precise definition or problem statement for CFD. We need to come up with aerothermal environments. And what we mean by aerothermal environments are temporal and spatial distributions of physical quantities that are required for selection, sizing, and testing/qualification of materials that make up thermal protection system. So what are the physical quantities of interest? Number one is pressure. Number two is a convective film coefficient. And the reason for convective film coefficient I'll get to in a bit. And you then would then load into it, whether it's laminar, transitional, turbulent, hot or cold wall, catalyticity, smooth or rough wall, all of that gets clubbed into the film coefficient. You then have to come up with a radiative heat flux number, if it's applicable. In the case of ice giants, it is not. And you need to come up with the recovery enthalpy. Essentially, what we are saying is, given a film coefficient and given a recovery enthalpy, the difference in enthalpy between the edge and wall is what drives the heat flux. And you can back out what the unblown convective heat flux is, which then goes into a material code, and the material code then alters what the wall enthalpy ought to be without changing the film coefficient. Now, optional quantity of interest is surface shear. Although we don't directly use that in the design of a thermal protection system, but we are cognizant of the fact that we have seen failure of materials at very high shear levels, or at least we attribute the failure to high shear levels. And usually you wouldn't want to exceed a number like, say, 4,000 Pascal anywhere on the heat shield. So we are chasing after these quantities that we need to extract from CFD. Well, we have a whole host of computing tools to go with the CFD. So since the grid is the CFD, you have to develop a grid for the geometry. There are umpteen software to do that. So most of them are commercial. But for simple geometries, like a 45-degree sphere cone, where you have rotational symmetry and no features in the forebody or the back shell, then you can use a simple tool called Capsule Grid to develop that volume mesh for you. Now, here's the issue. If you have rotational symmetry and no angle of attack, your life is much easier because you can limit yourself to axisymmetric calculations, and you do 3D calculations only at the very end. And that would be mostly to look for angle of attack variations. So you can very rapidly generate design databases in an axisymmetric mode. You now have a whole list of 3D and axisymmetric solvers that you could use for these specialized hypersonic applications. There's Deepler and US3D at NASA Ames, LoRa and Fun3D at NASA Langley. And then once you've computed the flow, you use B-layer to extract boundary layer data from the computed flow field. Radiation computations, you have Necker and Hara at the two field centers, Langley and Ames. You really don't need these for outer planet entries. And then you finally do need to push the imposed environments through material response, because you need to determine the size of the TPS material. Now, the tools you could use in sequence standalone, or in some cases, you might have to couple the tools, and the coupling could be loose or tight depending on the mission posture to certain things. Now, all that said, if there is substantial mass loss due to ablation, then trajectory codes too would have to be coupled in. And the only case would be Jovian entry, and we don't have to worry about that at all, at least much into distant future too, I'd assume. Now, features of these high temperature flow fields, codes. Of course, they handle chemistry and usually are flexible enough for you to define your own reaction mechanism and rates and test things out. They usually have good thermodynamic properties, either as curve fits or analytic expressions for both atomic species as well as molecular species. And if necessary, you would also want to consider free electrons. They have transport properties already ready-made. Those would be coefficients of mass diffusion, viscosity, and thermal conductivity, and these are usually based on collision integrals, so we have confidence in the data there. You have mixing rules for mixture properties. As far as thermodynamics goes, that is fairly cut and dried. As far as transport goes, there is some open issues. There are some open issues that you need to consider. There are umpteen models for turbulent transport of mass momentum energy. And more recently, there's a lot of work being done to include surface roughness in the mix so that you get an idea of how much heating augmentation you get due to the surface morphology. And they do have gas surface interaction models. Again, it depends on what level of fidelity you want in this interaction. My claim is gas surface interaction without a material response thrown in becomes a little dicey. And you would then need to consider blowing boundary conditions to consider injection of pyrolysis products into the TPS material. So all of these features more or less exist in the codes that we use for ice giants entries. So to give you an example, I'll walk you through some certain key features here. The probe geometry is shown in the left figure. It's a 1.26 Galileo size diameter, but it's much blunter than the Galileo shape. And the reason for blunting this shape is to reduce convective heating, because we know that radiative heating isn't a big issue. And this is for an entry probe into Uranus. On the right, you have the altitude velocity. That's the trajectory that the probe would fly. And I believe this is for a high heat load case. So this would be the one that determines the size of the TPS and hence the overall mass that you would add to this probe, the thermal protection mass. And it's all mostly for the heat shield only. Mind you, we have left the back shell out of the calculations. There's more things to consider in there. For initial purposes, we work with 3-DOF trajectories, so no capsule dynamics are involved. And the excuse me, the trajectory that's shown here is a a max heat load trajectory. And heat load here, what I mean by heat load is the time integral of heat flux. And the heat flux time history is usually almost 99.99% referenced to the stagnation point of the vehicle, which is the apex of the heat shield, or the 0, 0 point on the figure on the left. So once we have this trajectory, we do CFD calculations at the green points that are shown. So we have discretized that trajectory, and we know the density and velocity and temperature, the 3 key variables in your CFD calculations. We have the geometry and everything set up, and we compute using that. So what I'm going to show you next is for that particular geometry and that particular flight trajectory, I'm going to show you temperature profiles along the stagnation line for some points in the flight trajectory. And I will highlight a few things in the problem with wall boundary conditions. We will see what turbulent flow means, what transition means in there, and see how to go about getting turbulent conservative thickness estimates. So if you look at early time point, here's the point at which you can no longer claim that that total enthalpy is a constant past the shock. This is a low density flow, so you have enough dissipation in the outer layer. In fact, this is a case not just of a strongly interacting boundary layer, but it's more close to being a merged layer where there is no distinction between an inviscid part and a viscous part. So the top and bottom figures demarcated by the line, one represents the overall stagline profile, and the other is a magnification of it near the wall. Key thing in here is when you have a cold wall, you have a thinnest boundary layer. And as you heat up the wall, that thickening of the boundary layer due to wall heating also pushes the shock out. So the hot wall, whether it's fully catalytic, which is red, or hot wall in equilibrium, they are in close agreement, not too bad, but they're quite distinct from a cold wall prediction. The four figures on the right of the black line, those represent surface distributions of the four key variables, at least three key variables that you would need in sizing the material. For this particular time point, your stagnation point is the highest heating. The only anomalous behavior in the CFD is that the turbulent rough wall calculation is not distinguishable from a laminar one, whereas the turbulent smooth wall heating is higher. This I have not explored in greater depth, and my apologies for that. If I now go to a next time point where I expect to see peak heating, what I want you to focus on is the two figures to the left of the black line, at the left of the slide, top and bottom. One shows you the overall heat temperature profile along the stag line. What you see first on the top figure is the thermal overshoot with a rapid decrease towards an equilibrium level. And that thermal overshoot is essentially the chemical relaxation that's occurring behind the bow shock. However, if you look at the wall temperature, this is strange. If you had a fully catalytic wall in which you did not constrain the recombination process through an equilibrium constant, the wall temperature is higher than the sublimation temperature of carbon. That's one. And the gradient is now strange. You have the wall heating the gas rather than the gas heating the wall. For an equilibrium wall and a cold wall, it's not a problem. Cold wall, it's definitely not a problem because you know at 298 Kelvin, H plus H will go to completion to H2. There is no thermal barrier to that recombination reaction. So hot wall, in the absence of material response being included, you do have to take with a grain of salt. You do have to examine the solutions that you have. The more interesting thing is in the surface distributions to the right of the black line shown in the figure. And particularly what I want to draw your attention to is the dashed green line in film coefficient, which is a equilibrium hot wall with surface roughness included in the calculation. So you do see heating augmentation due to turbulent heating augmentation due to roughness, but the peak of that distribution is not necessarily on the conical flank. It occurs on the spherical nose or sphere section nose, a little ways away from the stagnation point. So between the conical flank and the spherical nose could end up being the driver in terms of material sizing, which I think indeed it is. So this is at the peak heating point, which you do need to worry about. And the second would be the peak dynamic pressure point. Now here, the post-shock temperatures are lower, which we knew was going to, in the previous case, your post-shock temperatures were less than 6,000 Kelvin. So at that temperature with those number densities, there's nothing to write home about in terms of radiative heating. And when you get to peak dynamic pressure, it's even better. It's like 4,000 Kelvin. But here too, At this point, you have persistence of your hot wall, fully catalytic hot wall temperature being strange, where it's the wall heating the boundary layer rather than boundary layer heating the wall. Whereas equilibrium wall has no issue. And in terms of turbulent heating, it's the roughness augmented heating that you worry about, and that peaks again on the nose of the geometry rather than on the conical flank. And by the time you get to a later trajectory, there is no chemical activity to talk about. At that point, the difference between a hot, fully catalytic wall or an equilibrium wall becomes moot. And again, your roughness augmented heating is on the nose and not on the conical flank. And indeed, when the calculations that we did in TPS sizing, we did look at these, and yes, it is the nose point away from the stagnation point that drives TPS sizing for this case. Finally, we'll look at surface distributions of a few key parameters here, and especially the cold wall heat fluxes, because you do not want to exceed a cold wall heat flux of 2.2 kilowatts per square centimeter, because that is a nice number that we can test to in the ground-based ArcJet. And we also want to make sure that the hot wall shear stress does not exceed 2 kilopascal. And we also want to see where if you had a typical roughness number of 0.4 mm, where is the REKK number exceed, where does REKK exceed 200? And we'll see that it occurs after peak heating, or close to, I think. First part, low density, there's really nothing to write home about here. The surface heat fluxes are low, surface shear stresses are low. And if you look at REKK, it says there is going to be no transition. You get to peak heating, your cold wall number is about 2200 watts per square centimeter. Your fully catalytic wall is strange, that distribution, but the equilibrium wall number is much lower. Okay. Here, if you look at REKK distribution along the surface of the capsule, you do not exceed 200 Kelvin. You approach it, you get close to it. So it's unlikely that you're going to have a turbulent transition due to roughness at peak heating. So whatever occurs would occur after it. So that helps you peg where you think you work with the fully turbulent environment versus where you would work with a fully laminar one. So when you get to peak dynamic pressure, now you have REKK well in excess of 200. Don't worry about the cold wall result. You don't really need to worry about REKK on a cold wall. You need to worry about REKK on a hot wall, and that you exceed on the nose itself. So you do have a fully, and so hence you would use a hot equilibrium hot wall number that's been augmented by surface roughness, which is the dashed lines shown in the heat flux distributions and shear distributions. The nice part is the shear stress distribution is still under my magic limit of 4 kilopascal, which was observed in the AETC ArcJet. And by the time you get to after peak dynamic pressure, things have started cooling off, but your boundary layer is still a turbulent boundary layer. So how well did we do in terms of taking these, the stagnation points and compare them back to correlation? And this is a reason for wanting to do this, and I'll get to that in the next couple of slides. We didn't do too badly. In terms of pressure and enthalpy, we are okay. The pressures are somewhat lower than what you would say would be rho v squared product. This is expected. I mean, rho v squared is actually a Newtonian impact value. So if you went to the modified Newtonian value, you should expect something lower than rho v squared. And usually that's of the order of 5% or so. The enthalpy values are lower, but again, boundary layer edge is not very well defined at low free stream densities. Now, the film coefficient is significantly lower than expected. That is, the predicted heat, because the predicted heat flux is lower, and there seems to be a time lag, a time shift in where that peak occurs and how quickly the rate of decrease of film coefficient shown in the middle figure is it does track with the correlation that's used, but the levels are lower. So overall, you would conclude that the correlation-based stag point and environments are conservative, but that's just the stag point. You don't get a sense of what the distributed heating is. And so you have to resort to CFD. You can't rely on stag point alone in doing calculations. So what are the uncertainties? And there are 4 of them that you need to worry about. And these uncertainties are usually handled as multipliers on CFD predictions. We claim that the pressure uncertainty is less than 10%. So we use a max multiplier of 1.1 on the CFD predicted pressure. For laminar heat flux, we say the uncertainty is less than 20% or so, which means the multiplier maximum is 20. For turbulent heat flux, we assume a 35% uncertainty. And all of these uncertainties are based on application of tools to other flight projects as well as to ground tests to give a rough idea of where the CFD might be under or over predicting these cases. In turbulent heat flux, we assign a 35% value. And the heat flux augmentation due to roughness is, I should qualify that and say turbulent heat flux augmentation due to roughness is roughly 30%. So you would factor all these uncertainties into what comes next. And that is using CFD results in system studies. Now, you've spent an enormous amount of time in computing flow fields, detailed flow fields for all kinds of configurations, etc. You can use these correlations. You can use these data to develop correlations and use them in help speed up early system studies. And the correlations usually are for a stagnation point, although we have tweaked that since to include off-stag points as well. The beauty of this is you can add the correlations into trajectory codes. And the nicer part is you can couple trajectory codes with 1D material response solver. So you have a self-contained initial sizing capability that you have because you have correlations that you could use, and you have a material response solver on which to apply these correlations to come up with 1D material thickness, 1D sizing at least. So it's very useful in early system studies. And the stagnation point scaling law for pressure is very, very simple. It doesn't matter. When I say scaling, it means I'm going to look at 3 variables, a aerothermal length scale, which I call R aerothermal raised to some exponent, an ambient free density raised to some exponent b, and the vehicle speed v infinity raised to another exponent c. So you can use your CFD data and correlate your heat flux number, your whatever quantity. You can correlate using this product, and you want to use such a correlation for pressure, convective heat flux, and for the case of ice giants and any, it would be enthalpy. You don't need to worry about radiative heat flux. Now, the reason you focus these on the stagnation point because there are additional theoretical considerations that will help shore up what correlations you come up with. For pressure, it's very, very simple. It's modified Newtonian theory. Its rho v squared product is what your stagnation point pressure is going to be, and you temper that with a factor F, and that factor F is between 0.9 and 1. There is no geometric scale involved in this scaling law. For convective heat flux, it's a different way of looking at it. You do have an aerothermal scale, and you know that your heat flux should go as 1 over square root of that. And you have your heat flux dependent on stagnation pressure and the enthalpy difference or enthalpy potential that drives that heat flux. This is a simplification of the Fay-Riddell correlation, which in turn is also based on boundary layer type, at least type point CFD calculations for various different combination of parameters. Point here is you have to be careful in extrapolating this correlation. It assumes first order boundary layer theory. That is, you have a very thin shear layer, much smaller than the shock standoff distance, attached to the wall and is driven simply by the inviscid streamwise pressure gradient. Now, this correlation has been revisited several times by Zobe, which we use in ArcJet testing, Dyward and Marvin, and then Sutton and Graves. And these correlations were developed in the 60s and 70s. While the constants that we use today might be a little different than what's in these published data, the fact is the form of these correlations are still in use today. So we know there is a geometric scale. We require a enthalpy difference that drives that heating. And the constant K that's shown in here, it depends both on the gas mixture and the choice or transport property model. So if you used Wilke's mixing rule or Gupta-Yost mixing rule, you would end up with K values that are different. Now, the reason for taking this Q-stag this way is I can divide Q-stag by the enthalpy difference. I have a film coefficient, and the film coefficient at the stag point simply depends on the stagnation pressure and the aerothermal length scale. Nice part of this is the film coefficient in the first approximation is independent of the wall type, cold versus hot, and depends solely on the stagnation pressure and the length scale. So which means the convective film coefficient peaks when the stagnation pressure peaks. Now, stagnation pressure peaks a few seconds after convective heating peaks. So when you include material thermal response, the true peak heating point will lie between the two ideals. One ideal is the peak convective heating point, and the other ideal is the peak dynamic pressure point. Now, the edge enthalpy that you require for a stagnation point is simply the free stream enthalpy, provided, of course, that your boundary layer assumption is valid. That is, you have a boundary layer thickness that is significantly smaller than the shock layer thickness. At the stagnation point, you do not need to make the distinction between edge enthalpy and recovery enthalpy. So we have this capability. Now, if I took the calculations that we had done previously and plonked them into these two types of plots, the plot on the left is simply the scaled heat flux shown by square root nose radius by square root P stag versus the enthalpy difference. They line up in a straight line. The line that you have to be skeptical about is the red line. That's the one that is based on a fully catalytic wall assumption where the wall temperature did something really funky at the wall, where the gradient looked strange. But the cold wall and equilibrium wall line up very nicely with each other. And that value is different than the Sutton-Graves value that one would use. And to me, the primary reason for that is the choice of transport model that was used in Sutton-Graves work versus what we use today. Now, to make these useful for even more rapid work in a trajectory code, We simply work out what the cold wall heat flux ought to be. So you plot Q stagnation versus the product on the left, and that should line up as a straight line. And sure enough, more or less, things do line up, and we have a usable correlation that we can put into a trajectory code. The application of this correlation-based methodology comes in handy when you're doing rapid trade studies. So if you take an example of heat material, it can be manufactured on one of two looms. Loom 1 is the basic loom that you would use, and Loom 2 would be a specialized, more expensive way of manufacturing the material, and the material manufacturer makes it narrower as well. So for a range of ballistic coefficients and entry flight path angles into Saturn, Uranus, and Neptune, you can work out what the stagnation point sizing ought to be and see where those points lie within this loom space. Now, when we say loom, remember, heat is a two-layer TPS material. It has an outer dense layer, which we call the recession layer, and an inner less dense layer, which we call insulation layer. It's essentially woven carbon, 3D woven carbon fiber, into which you impregnate with phenolic resin. And all of that is taken care of underneath your trajectory calculations by a material response solver, FIAT, which is coupled in with our trajectory called TRAJ. And the neat point here is that we get an idea of what thicknesses we would need, what ballistic coefficients we should target. So essentially that puts a limit on what the entry mass ought to be for this entry velocity and cone sphere, 45-degree sphere cone shape, and what flight path angle would you need to be at to get underneath this loom shape. Now, a loom constraint. Now you can refine this further by putting in the maximum pressure that you can test at and maximum heat flux that you can test at, and you can carve out a usable space for this material. So that's where the application of CFD comes in into rapid initial design, which you can then parlay into a much more detailed design for a given configuration. So in closing, I'd say, from my perspective, given the simplicity of the number of species and size of the problem, the CFD for ice giant atmospheric entries is fairly straightforward with the tools that we currently have. What we do need to pay attention to are thermodynamic properties, which need extension down to 50 Kelvin. And the problem gets complicated because of the ortho and para forms of hydrogen. Transport properties need to be examined again because in light of inflections that we see in temperature variation, I really don't get the science behind that, and that needs to be examined. For Neptune, I would say CH4 kinetics would be important, even if the mass fraction is low. And the reason for that is the dissociation of CH4 leads to formation of radicals, and radicals are very reactive, and you get fast reactions from those. The gas surface interaction of atomic hydrogen with hot carbon, I think, needs to be addressed. I think what we have currently is inadequate. The other open issues are transition and turbulence and the influence of surface roughness. Although I've shown results here for turbulent heating augmentation due to surface roughness, you have to bear in mind that those are for the Baldwin-Lomax model with modifications to some of the modeling constants, if you will. We need other models, other approaches to either clarify what we've done or to negate them and come up with something better. We really also need to look at the fluid dynamics and chemistry of wall blowing because you have pyrolysis gases blowing into the stream. Now, this entire talk has focused only on the primary heat shield because that is where most of the thermal protection work goes in. You also have to be cognizant of backshell environments, and the backshell can get to be slightly dicey, especially at high altitudes, because you have low temperatures in the wake. You need to worry about that as well. And the shape of the backshell needs to be brought into consideration. And with that, I will stop and I'd be happy to take any questions. And this talk came from the Entry Systems and Technology Division at Ames Research Center. I cannot see the chat window.
Great. Thank you so much, Dinesh. That was a really good talk, overview of all the different issues involved for designing capsules, at least aerothermodynamics wise. We do have a couple of questions in the chat, so if you want, I can read them to you.
Yeah, how do I bring up the chat window? I can't see the chat window.
For me, it's over on the right-hand side. There's like a little chat drop down that you might have to click.
Okay, I think it's easier if you read it to me.
Okay. So this first one is from Eric Lira. You mentioned the Fiat code. Do you have a material model for cork? Has it been anchored with ascent heating measured flight temperatures?
Okay, now that I'm out of my depth on that one. I would say yes, there is a model for cork. I know it was worked on. I don't know whether it's been anchored. Okay, it was used, I think, in the ascent part of the abort motor part of the Orion program. I think it's been improved. I'd say that question is best directed to Mairead Stackpole of the Thermal Protection Branch at Ames. You would get a more definitive and clearer answer than one from me. Sorry, I don't know enough about material response here.
Okay. Yeah. So he says, please type the contact name and email address if you have it.
If I can find the chat window, sure.
Right.
I'm unable to find it. Oh man. Do I quit sharing and maybe it'll show?
I'm honestly not sure.
It hides when you share. There's a way to get it down, but if you don't find the exact place to place your cursor, you won't get it. So if you stop sharing, it's easier.
So should I stop sharing then?
Yeah, stop sharing. It should pop back up.
So Arno came to your rescue. He gave his email address for Eric.
All right, Arno, I owe you a donut.
So we have another question from Paolo Vendito. A fully catalytic wall has gamma equal to 1, which means that all the particles of species impinging on the surface recombine at the wall. This assumption is often made for conservative reasons, especially missions to Mars. In the light of flight data, which show much lower impact than predicted, can this assumption be relaxed in some way?
Well, okay. In the context of Mars, it's a different issue. But in the context of ice giant entries, I believe there is really no issue in terms of H plus H going to H2 up to a level. The thing is the giant planets are not oxidizing environments; they are reducing environments. The only real issue is that of hydrogen atom and its interaction with hot carbon. There's been work done in the past for Galileo entries, and that needs to be translated in here. So I would say gamma equals 1 is okay for ice giant entries. But then again, to hedge our bet, I would do a slew of gammas, easy to do, and the heat flux is going to drop as a sigmoid. Some being peak value at gamma equals 1, then I think it turns over at like gamma of 0.3 or 0.4, like a half order of magnitude decrease in gamma, then turns the heat flux down rapidly. And then you don't acquire any more benefits after gamma of 0.01 or so. It's almost a linear drop off, if I remember correctly. Two different things for CO2 environment versus hydrogen helium environment. You're right. For CO2 environments, there's a disconnect between what we predict for design purposes and what we do post-flight. But then there's a material involved in there, and we need to understand pica with whatever coating is on it to see what drives it. And the real reason for decrease is the lack of O plus O recombination at the surface, more so than CO oxidation. If you have a glassy surface, then you could reduce the amount of oxygen recombination, which is essentially shuttle tile principle.
Again, have you been able to anchor your heating prediction techniques for atmospheres other than Earth with real data?
Yes and no. Okay. Anchoring means, to me, anchoring means experimental data. There are hydrogen helium experiments from the past. I think Yee and Bailey in the 60s might have done those experiments in the ballistics range. And I think Vince Zobe did correlate those data. And I believe the CFD results track with those. I have not co-plotted them. I have to find them in some presentation that's buried somewhere on my Mac, but I can dig that out and get back to you. That I believe is true. Again, up to a certain enthalpy level, not beyond. But I think the enthalpy levels that are suitable for ice giant entries, I think yes. For enthalpy levels that are Jupiter-like, I don't believe there exists data at that high enthalpy level. But yes, there are data from the ballistics range in the past.